This is the construct. It's our loading program. We can load anything from slides to equipment, animations, training simulations, anything we need. That's right. We are going to look deep inside computer programs. The matrix is a system, Neo. That system is not our enemy. But when you're inside, you look around, what do you see? Fourier transforms, rotations, fully connected layers of a neural network, convolutions. The very essence of the methods that we're trying to teach. But until we do, they are still part of a complex system. And that makes them look like our enemy. You have to understand, most of these methods are not readily understood. And many of them are so entangled, so hopelessly intertwined in linear systems that they look like willing to fight your comprehension. Do you want to know what it is? The matrix is everywhere. It is all around us, even now in this very room. You can see it when you look at your windows or when you turn on your television. You can feel it when you go to work, when you go play video games, or when you pay your taxes. It is the world that has been pulled over your eyes to blind you from the map. Open your mind and step into the matrix, for it is here where illusions unravel to reveal the hidden truths behind every transformation. These are the conventions, Neo. The language in which the oracle, your professor, converses with the matrix. We write scalars as italic lowercase letters, symbols like A, B, or C in the realm of real numbers R. Next, we invoke vectors with bold lowercase letters, A, U, and V, each living in a vector space RD. Finally, we represent matrices with bold uppercase letters, A, sigma, and U. Their realm is two-dimensional, R, M times N. Heed these forms well. They are the keys by which you unlock the deeper levels of the matrix. Look closer and you'll see that what we typically call a vector is but a specialized matrix. Observe this column vector V, a matrix of height m and width 1, holding elements v1, v2, and so forth until we reach vm. Yet, if we lay that same structure on its side, we obtain a row vector whose transpose ut arrayed as u1, u2, and so forth until we reach un, which reveals a single row of elements. In the matrix, remember, appearances can be deceiving, and the difference between row and column often lies in a mere rotation of perspective. Now behold this entity, the matrix A, an m times n tapestry of numbers woven into rows and columns. Each element, Aij, aligns to form a grid of numbers. A11, A12, and so forth to A1n in the first row, and A21 to A2n in the second row, and so forth to the last row, AM1 to AMN. But there is more. We can also see A as a band of column vectors, A1, A2, all the way to AN. Each vector is a pillar, a distinct slice of the matrix, and together they reveal the full structure, showing us that is hidden within every arrangement is another way to perceive it. And behold, the same A also reveals itself as a collection of row vectors stacked one atop another. Each row, A1 transpose, A2 transpose, and forth to AM transpose, is a single slice, a horizontal band of information. When these bands unite, they reconstitute the matrix from another vantage point, reminding us that within the matrix, what appears solid and unchanging can instead be reinterpreted from multiple angles, revealing fresh perspectives in our journey. Now gaze upon this, the sacred operations. The matrix is not a mere collection of numbers. It is a realm where the laws of addition, scalar multiplication, and matrix multiplication govern all. You will see that to add two matrices, they must conform to the same shape, like partners in a dance. But multiplication, this is where the true power lies. It is not enough to simply align. The rows and columns must meet in a rhythm, like two forces of nature converging. Now focus your attention on the multiplication of a vector. A new vector emerges, brought forth from the union of these entities, reshaping everything in its path. Observe matrix A as a collection of columns A1, A2 to AN. When A multiplies X, each component X1 to Xn in X selects and scales one column each. Summed together, these scaled columns fuse into A times X, a new vector. This reveals the deeper truth. Matrix vector multiplication is the linear combination of all those column pillars, weighted by the entities of X. The hidden power that let us bend or shift our world inside the matrix. Witness the essence of matrix vector multiplication. When A meets X, the column A1 is scaled with X1, A2 with X2, all the way to AN scaled with XN, and then fused into a single vector. Mathematically, we see this equals to a sum over J from 1 till the end of the columns. This illustrates a vital truth. Behind every multiplication lies a linear combination of columns, each representing a part of the matrix woven together by the entries of X. Envision A as a compact piece of code, where each column AJ stands as a subroutine designed to linearly shape your n-dimensional input. When you multiply A with the vector X, you're effectively chaining these subroutines. Each column's influence is scaled by the corresponding entry in X, and the resulting transformations conspire to yield an m-dimensional output. In this way, the matrix processes your input piece by piece, weaving together a new form. When the oracle's code grows tangled and hidden, remember how to uncover the underlying subroutines. We apply the standard basis vectors E1 to decipher the first column and E2 for the second. As each EI has a single 1 in the ith position and zeros elsewhere, feed one of these vectors into A, and the only surviving subroutine is AI. So A times EI equals AI. Like keys to a puzzle box, each basis vector extracts exactly one thread of the matrix, revealing the hidden transformation contained in that column. Observe when X equals E2, the second basis vector, and matrix A and columns, E2's solitary 1 highlights A2 and zeroes out every other column. Thus, A times E2 equals A2. In the matrix, this single input pinpoints exactly one hidden subroutine, reaffirming that by selectively activating each entry of X, we command which columns of A come to life. So with the entire set of basis vector keys, we are able to decipher any linear subroutine, even from layers of unknown code or APIs. Turn your gaze to the 2D rotation matrix, R theta, which revolutes vectors counterclockwise by angle theta. Written as R theta equals cosine theta minus sine theta, cosine theta, this transformation preserves the magnitude of any vector, its length, and relative angles remain unchanged as it spins. Here in the matrix, it serves as a gateway to reorient perceptions without distorting the essential structure. Observe how R theta ushers each basis vector into a new orientation. E1 equals to 1, 0 migrates to cosine theta, sine theta, while E2 equals to 0, 1 shifts to minus sine theta, cosine theta. It is a perfect demonstration that the rotation matrix recalibrates direction while preserving length, each vector pivoting by the same angle theta around the origin, all without distorting its magnitude. Visualize E1 pivoting gracefully by 45 degrees or swirling a full 90 degrees. As you can see on the grid, each rotation lifts E1 away from the x-axis, preserving its length, but altering its direction. The angles minus 45 degrees, 90 degrees, or even 110 degrees are simply different by rotations via R theta, reminding us that when navigating the matrix of linear transformations, every turn is exact, every magnitude remains intact, and geometry is our guide through these illusions. Now we pose a question to the matrix. Among all possible input vectors n, confined to the unit circle, with length equals to 1, which one yields the greatest length when transformed by A? In other words, we seek to maximize the norm A times n to the power of 2. As we sweep across the circle, we watch how A stretches each direction differently. The vector that attains the maximum norm is the direction of greatest amplification, where the matrix distorts most powerfully without breaking the unit constraint. Witness the power of A as it transforms the unit circle. Using matrix A into an ellipse, each point on the circle is stretched or squashed by a different factor, revealing elongated axes in red that mark the directions of maximum and minimum pull. These directions act like hidden channels of the matrix, dictating how A distorts space. Where once we had uniform distance from the origin, we now see an ellipse, a geometric fingerprint of the transformation's influence. Now travel deeper into the heart of the matrix, where we reveal that every matrix, like any good illusion, has its inverse. But beware, not all matrices have one. Only those with full rank, those whose columns and rows span the entire space, hold the magical key to flipping the transformation back. When that key is found, the matrix bends backwards, and what once was reshaped can be returned to its original form. But the matrix has many instances, and not all of them have numbers of columns and rows identical. How can we unravel their secrets? Now, as though guided by the keymaker himself, we unlock a deeper level of the matrix through the singular value decomposition, SVD. In this grand unraveling, any matrix A can be decomposed into 3 pieces. A equals to U sigma V transpose, where U and V are orthogonal matrices, like well-tuned gates that carry the left and right singular vectors. Sigma is a diagonal matrix that holds the singular values, the very codes that control how A stretches or squeezes each direction. By wielding the SVD, you peer into A's core and see how it disassembles and reassembles signals, revealing the fundamental directions, those with the greatest influence and those that vanish into the margins. In short, the SVD is your key to navigating and mastering the hidden architecture of the matrix. Through the lens of SVD, we glimpse how A reshapes space. The columns of U illuminate the key directions in the input domain. Their orthonormal nature means they stand as perfectly perpendicular axes through which A funnels any incoming vector. Next, the diagonal entries of sigma are the singular values, magnifications or attenuations that dictate how vastly each direction is scaled. Finally, the columns of V mark the output space directions, to which these scaling factors lead. Together, U, sigma, and V form the compass, measuring stick, and final orientation that guide us through every transformation the matrix performs. Observe the three-step choreography of the SVD in action. First, U reorients the original circle, like a swift rotation aligning us with new axes. Next, sigma applies distinct scalings along these axes, stretching or shrinking each dimension until the circle transforms into an ellipse. Finally, V transpose again repositions the ellipse into its final orientation. Together, these stages unveil precisely how A contorts its input. One rotation, one scaling, and then another rotation to achieve the ultimate configuration in the matrix. This is how every matrix operates. With SVD, we can understand any instance of the matrix. When the matrix has missing dimensions, when A fails to span all of its possible directions, we speak of rank deficiency. In this scenario, A can't quite transform vectors into all corners of its range. Some directions collapse or disappear. By applying the SVD, we lay out the singular values in descending order within sigma. Those that dwindle to zero or near zero unmask the lost dimensions. In this way, the SVD reveals whether A is complete in its reach or if it's hiding dormant directions that fade into the background. When a singular value is zero, it exposes a hidden dead zone in the transformation, an entire dimension that is crushed to nothingness. In 2 dimensions, for instance, a unit circle might flatten into a line segment, or even a single point, if both singular values are zero. Thus, matrix sigma with entries like sigma 1 and 0 reflects a reality where one direction remains vibrant while the other is collapsed. In the matrix, this is how certain pathways vanish, stripping away degrees of freedom and leaving us with a flattened rendition of the original shape. Here the full power of SVD is revealed. U conceptually repositions our axis system without affecting the shape itself. So the circle remains a circle, but in a new rotated coordinate view. Next, sigma applies an extreme scaling. One dimension shrinks to zero, morphing that once proud circle into a mere line, a degenerated ellipse. Finally, V transpose again rotates this collapsed shape into its final orientation. In this rank-deficient world of the matrix, entire dimensions can vanish under sigma, leaving behind only a flattened relic of the original geometry, limiting our options. Here we see the grand finale of our circle collapsing into a mere line, demonstrating how a single direction can be stretched while another vanishes entirely. Yet even this profound glimpse into the matrix leaves part of its essence concealed. SVD shines a brilliant light on how A transforms space without intrinsic properties of A may remain hidden. No matter how many times we apply the matrix, it will always hold mysteries that lurk beyond the reach of our algorithms, reminding us that in this world of linear transformations, revelation does not come without the right key. Beyond its power to decompose and reveal structure, SVD also bestows computational stability. When A has small singular values, even minor perturbations can spark wild fluctuations in the output, hinting at numerical fragility. Here, the pseudo-inverse A plus equals to V sigma pseudo-inverse U transpose rides to our aid. In the pseudo-inverse of matrix sigma, we effectively invert the non-zero singular values with 1 over sigma I, while those that are 0 stay locked at 0, preventing division by nothingness. This careful handling of 0 or near-zero singular values tames runaway instabilities, offering a more stable pathway through the matrix, especially when A is rank deficient or ill-conditioned. Witness how pseudo-inverse A strives to undo A's compression. Though it can properly invert the still active dimension, the collapsed axis remains irretrievable. Its singular value is permanently 0. Thus, the lost dimensions cannot reappear. Once the matrix has flattened a dimension, no inversion alone can resurrect it. In other words, the pseudo-inverse can save what's left but cannot restore the original information erased. In truth, this power of the SVD extends far beyond mere theory. It emerges in real-world applications like noise reduction, image compression, and feature extraction, where carefully trimming small singular values can clarify signals or reduce data to its most meaningful components. When noise about epsilon rank provides a threshold to deem which singular values are significant. Thus, instead of counting only exactly non-zero singular values, we count those larger than a tolerance epsilon. As always in the matrix, small details matter. Setting epsilon wisely ensures we capture the true dimensions, carrying genuine information while discarding the illusions of noise. In the matrix, factorization techniques are powerful tools for unraveling linear systems and revealing hidden structures. SVD in particular stands as a robust and elegant way to decompose any matrix. Beyond the visual transformation we've seen, factorization also proves crucial in real-world problems, from refining regression solutions where we can minimize errors with precision, to fueling more efficient computational algorithms. Whether you're reconstructing signals or solving massive systems of equations, these factorization methods act like well-chosen keys, unlocking the potential of data while maintaining numerical stability in the face of complexity. Now enter the realm of linear regression, where our goal is to model the bond between a dependent variable y and an independent variable x. We seek a line y equals m times x plus t that best predicts y based on x. This is, in essence, another fragment of the matrix, one where data points shape the slope m and intercept t. Our aim? To glean the underlying pattern, the hidden relationship, so that with every new value of x we can peer ahead and foresee its corresponding y. As new observations xi, yi stream into the matrix, our mission is to uncover the slope m and intercept t that minimize the gap between predicted values y hat I equals to mxi plus t and the actual yi. Mathematically, we write y equals to m times x plus t. For multiple data points, we can bundle everything into vectors and matrices, turning this problem into a linear system, where we again see how the language of vectors and matrices provides a powerful toolkit for revealing hidden structure in the data. Behold our data points xi, yi laid out in front of you on the plane. Each red mark signals a measured observation, tangible evidence of how y might depend on x. Gathered into a neat column structure, these pairs become a portal into the regression problem. We aim to transform these raw coordinates into a best fit line. As always, the matrix welcomes us to recast them in linear algebra form using vectors and matrices as our guiding framework to find M and T. This is how we bring order to the swarm of data, seeking the simplest relationship woven into these points. Observe how we reshape this reality using matrices and vectors into a linear system. We construct our design matrix M to capture both the feature values xi in the first column and the column of ones for the intercept term. Stacked into M, these data points form the grid upon which we seek our line. Meanwhile, the parameter vector b equals to m and t contains the slope and intercept of our hidden codes to be unveiled. Thus, above equation y equals to m times b embodies our overdetermined system. Typically, more data points than parameters compel us to look for the best fit in a least squares sense, rather than an exact solution. The matrix once again guides us, placing data in one hand and parameters in the other, ready to fuse them via linear algebra. Now, as we crack open the regression problem, we harness SVD to decompose M into U, sigma, and V transpose. Observe the pseudo-inverse of M computed by a standard library provided by your operator. With its help, we can solve for the parameters b by multiplying with vector y. Here, y is our vector of observed outputs, 2, 4, 6, 7, 9. Thus, SVD becomes our gateway to a precise line-fitting solution, slicing through the data with minimal total error, revealing the slope and intercept that best replicate the observed points. In this manner, we see yet another way the matrix and its transformations can clarify the fog of real-world measurements. Here, the final multiplication, b equals to pseudo-inverse of m times y, reveals the slope m and intercept t. Plugging in our numbers, we find b equals to 1.7 and 0.5. which means that our best line fit is y equals to 1.7x plus 0.5. Thus, in the matrix of data points, this line offers a crisp, linear approximation of how y evolves with x. And all of it, once again, is orchestrated by the power of the pseudo-inverse in harmony with SVD. Behold the final result, the line y equals 1.7x plus 0.5, gracefully threading through our data points xi, yi. Each red circle now hovers near our fitted line, validating that we have extracted the signal from the noise. In the matrix of regression, we have gleaned a linear rule that predicts y from x with minimal discrepancy, yet another illustration of how fundamental transformations and factorizations can transform scattered observations into a coherent relationship. In the grand tapestry of linear algebra, the SVD offers a steadfast beacon, especially in overdetermined settings, where more equations than unknowns threaten to destabilize our journey. By artfully dissecting M into U, sigma, and V transpose, we gain numerical resilience in the face of noisy, sprawling data. Small wonder, it's championed across so many fields. From data analytics to cutting-edge research, its methodological insights keep our regression solutions honest, stable, and thoroughly grounded. Thus, we conclude our traversal of the matrix knowing that in every twist of dimensionality, the SVD stands ready, guarding both clarity and order in our transformations. SVD's influence travels far and wide, from signal processing, where it helps to denoise and clarify signals, to data compression, distilling essential features from sprawling information, and to principal component analysis, PCA, unveiling principal directions in multidimensional data. By dissecting any matrix into its fundamental components, SVD allows us to see past the clutter and extract core structures. In this sense, understanding SVD is like holding a master key within the matrix, unlocking patterns across diverse fields and granting deeper insight into the nature of transformations. Remember, this revelation is but a threshold. With the SVD, you have witnessed how a matrix conceals its essence, rotating, stretching, and collapsing dimensions with precision. You have glimpsed the power that emerges when we decipher these transformations. Yet beyond this doorway lies an even deeper stratum, a realm where eigenvalues and singular values converge, and the full complexity of the matrix awaits. Step forward if you dare.